Okay. Okay, so I can start again. So, hi everyone. So I am AI engineer at AMBOSS, and I have a background in informatics and machine learning. I did my my bachelor at the University of Rome in Tor Vergata, and I did my master in informatics, and I did some specialization in artificial intelligence. And then in the last years, I've been working for medical startups. In particular, I've been working for Ada Health, and since a couple of years, I'm at AMBOSS. Overall, I've been almost 10 years abroad, and now I just moved back. I'm very excited about this. In general, about me, you can say that I'm a nerd. I love artificial intelligence, but I also love humans and nature. And this is a picture of a fox, and my last name is Volpi, so you can understand why I took it. This picture, I took it in Patagonia last year before COVID. This was very nice. So what do I do at AMBOSS? As I said before, I'm an AI engineer. AI engineer is a combination between data science and backend engineering. So what we are doing is we are using the data to explore some problems, and we understand we're trying to deliver an AI solution to this problem. And I work in a team at AMBOSS which is called Knowledge Access, and we are a cross-functional team. We have a backend, front-end, and other AI engineers as me, and we have the mission to provide fast and reliable access to our knowledge base. Besides that, I'm also a chapter lead for AI engineering. So I'm advocating for the use of AI in the company, and I facilitate the work and the personal development of the other chapter members. And I'm also helping AMBOSS in establishing a new tech hub here in Cagliari, and this is very exciting, and we're gonna say a little bit more about it later. And this is what we are aiming to do here in Cagliari. So we want to contribute to the local tech ecosystem, and we want to make this the next tech hub in Europe. And you might ask yourself, what is AMBOSS? So this is our mission. So we want to empower all doctors to provide the best possible care. The company was established in 2012, so some time ago. But we reached very, very quickly 95% market share with German students. So basically, almost most of the physicians that graduate, they use our platform to prepare their examinations. But we also launched an English version, and we reached 60% of our market share with the US students. Our focus is to build a platform for medical students, but also clinical support for physicians. And we have more than 450 employees from 40 different countries and offices in Berlin, New York, and now Cagliari, as I just mentioned. So this is what the
Audio Jungle
for looks like. So basically, the students can
Audio Jungle
in which they are and they can answer with they are wrong.
Audio Jungle
Why is it wrong? And for physicians, it's slightly different. We basically trying to give the physicians
AMBOSS helps physicians make confident decisions with smart clinical tools designed for clinicians on the go. We know you're overloaded with information and working crazy hours. Our editorial team of physicians thinks just like you when choosing every word of our content. Find management checklists,
medical,
diagnostic algorithms, red
editors,
flag signs, differential
and,
diagnoses,
here they
emergency
can-
evaluation,
can open
drug
articles
dosing, and
about
other clinical
different
content you can trust.
diseases, and
Over
then they can
35,000
see
physicians
what
use
is the-
AMBOSS for clinical
what
decision
is the
support.
treatment
Start
or the
today.
differential diagnosis for different diseases. So
AMBOSS helps physicians make confident decisions with smart clinical tools designed for clinicians on the go.
Our mission. And as you open AMBOSS, you might see different parts. So as we've seen, we have the possibility to create questions, but also we have articles, and then we have the search, which is at the top. And the search is by our research. It's actually the most used feature after login. And this is coming from a heat map on where users click after the login, and that's why we focused our efforts in building a better search for AMBOSS, because this can become also a clinical decision support system for the users. And this is how the AMBOSS search used to look like before. So user would search for HIV, for instance, which is, of course, a disease. And they will get like a first result, like a result that points to our HIV article, which is the top result, as you also can see from the little icon here. But then in the old AMBOSS search, they would also get like the same result repeated once, and then they will get like a bunch of completely irrelevant results. And these results contain the word archive, for instance. And you might wonder why the hell these articles appeared here when someone searched for HIV. And the reason why they appear is that actually, archive contains the word HIV, contains the letters HIV, and that's why we were retrieving them. So as you can see, there was some issues in this old search. And that's why in 2020, my team, the knowledge access team, decided to rebuild the search functionality of AMBOSS from scratch. We used the completely new technology. We developed a microservice based on Python, and we used the Elasticsearch as the main search engine functionality. And we also use the relevancy-driven approach. I'm gonna say a little bit more what that means. And we also integrated parts of natural language processing and AI to actually make the search more intelligent. And this is what I'm gonna talk about today. So this is how it looks like, the new search. So the user will search, imagine that they will start typing in the search bar for AST, and they will get a list of suggestions. At the beginning, they might get like the first three results, these are, we call them instant results. So they go directly into the AMBOSS content, and they point to specific parts of the AMBOSS content. And then we have a list of suggestions which is used for completions, and they help the users to actually start basically defining what they're actually searching for. And then if they search for some of these, they get to this search result page, in which you have different elements. So you have like an immediate definition, what is, in this case, what is asthma, and also you get like instant, like the links to the content, but also you have a selection of relevant results mixed. So in this case, for instance, we have a guideline for doctors about asthma treatment, but you also get like images and videos of the treatment for asthma. And as I mentioned, there are different types, different document types that you could search. And we have articles, we have medical guidelines, we have the media, images and video, and we have also pharmaceutical drugs. But then it comes to the question, okay, we get to these results. So these are all the articles. And we need to find what is the right order of these results. Because the order, of course, is very important. And the users, especially physicians, they don't have a lot of time when they search something. They actually need to select something. And the first results need to be important. They need to be relevant, right? And this problem is called, in information retrieval systems, is called ranking. And I just want to give you kind of explain a little bit how the usual ranking, the usual way of doing it works. You're probably already familiar with this, but just as a refresher. So imagine you have a list of documents, and the documents might have different fields. So you might have a field which is a title, and a field which is a type. And imagine you have a title: heart attack, shark attack, heart block, and pneumonia. And the basic data structure which powers a search engine is called an inverted index. So what we do is that we take all the tokens, all the terms of the title fields in this case, and we create different rows for these terms. So in this case, we have heart as a term, shark, attack, and so on. And then as columns, we have the documents. So in this case, we put like some X whenever actually the document is, whenever the token, the term is mentioned in that document. So in this case, for heart attack, so we say that for the first document, which is the first column, the two tokens heart and the token attack have X. And this allows us to perform a very basic search, which is a Boolean search. So whenever someone will search for heart, for instance, they will get, we can actually look into the first row, the row containing the token heart. And this, as a Boolean search, we will return the documents 1 and documents 3, which contain the term, without a particular order. In order to actually get the ranking, so the order of these results, we do a slight variation of this, in which we take the term frequency. So we count the frequency of tokens in each for the documents. And in this example, we will put just 1 for each one of these, because we only have it. It's mentioned only one time for each document. But imagine that we modify the first document to be, instead of heart attack, just heart attack. And in this case, this will become a 2. And now the ranking with the term frequency would be heart attack and then heart block. This would be the first ranking. In reality, it is even a little bit more complex than this, because we're using something called TF-IDF, which is term frequency inverse document frequency. And basically we penalize the words which appear very often for all the documents. So words which have not a lot of meaning, such as D or whatever other small words, they will not be considered very, very frequently. So why did I spend some time to talk about this? Because I wanted to make you aware that generally all the search engines that you use every day in your life, usually they're built just like this. So it's a combination of TF-IDF scores for different fields of the document. So whenever you perform searches in some e-commerce websites, most of the time you will get results based on these scores. But we can make it better. And going back to this example here, we need to find a way to actually measure the relevance of documents. We need to find ways of answering questions such as when is the search result relevant for our users, or how can we assess that our search engine works all the time, both for simple queries such as ASMA, but also for complex queries containing many different terms or more complex questions. And also we want to know what complexity does the medical field in particular, in the case of AMBOSS, add to this problem. And at AMBOSS, we are using an approach which is relevancy based. And what it means is that we basically we use our main asset. We use our doctors to actually give us support and help us to understand how good is our search engine, how relevant are generally the results for the users. And for doing that, we adopted a tool which is called Cupid, which is used to measure the search relevance. And basically what we are doing is that we are taking a bunch of queries, which are real user queries. We take, of course, only a sample of all the queries of all the users that are performing searches on AMBOSS. And we collect these queries and we put them in this tool. And in this example, for instance, we have clinical neurology, Murphy symptom, shoulder, and so on. These are all queries that our users are using AMBOSS for getting their answers. And we ask the doctors to basically give a relevance score to each one of these results. So the results which you see here, these are coming from our search engine. And for the query, for instance, fracture first aid, you will get as first result conservative treatment of fractures, vertebral fractures, and ankle fracture, for instance. And then the doctor, our labeler, would give a relevance score from 1 to 10 to each one of these results. And what do we do with these labels? We use them to compute something which are called rank evaluation metrics. So metrics such as precision, recall, NDCG, mean reciprocal rank, and expected reciprocal rank, which we plot in this graph, and we measure every day. So every day we measure how are the metrics evolving, how are the metrics changing. And we do this to actually evaluate the impact of the changes that we make to the search engine, to know that overall, from a probabilistic point of view, the engine is not degrading their performance, but it's stable, or hopefully it actually improves. The changes that we're making are actually improving the overall performance of the search engine. So does it sound familiar? We are getting labels. We are doing something with these labels. Qualcuno ha idea di cosa possa indicare? Siamo in un meetup che si chiama? Carmine, aiutami tu. Esattamente. Actually, we could use this to create a supervised learning system, because we have labeled data, and we have like the kind of expected result, expected prediction, right? So we could actually think of automating this process and make the ranking not based on TF-IDF, but actually based on these labels, on what actually we collect with our editors, with our medical doctors. And there is a process for doing this in information retrieval, which is called the learning to rank. And the idea is that we can basically learning the best rank according to the labels that we collect. So this is a technique between machine learning and information retrieval, as I said, which is using the data to learn the best ranking. And the training data can be from explicit judgment list, as you've seen, but it could also become from implicit signals, which we collect from users. And this is how a typical learning to rank workflow looks like. So we collect these judgments, we enhance these judgments with some features based on the combinations of query and documents. And then we create basically, we can actually train a classification model or regression model according to the type of machine learning algorithm that we want to apply. And then we basically apply this to the results to actually show users the best possible ranking for their searches. And we have used at AMBOSS something a little bit like an evolution of the learning to rank systems that we've seen before, which is called the click models. So the click models are used to automate this learning to rank using just implicit data. So the implicit data that we're using is like the clicks and the skips signals from the users. So we see whenever someone is searching for something, whenever some user is searching for something, what results do they actually click on? So we are working under the assumption that so whatever a user clicks, it means that this is a relevant result for them. And whatever they skip, so all the results that are above that result that they clicked, is actually not relevant, is actually not good for the user. And basically, we can use this to actually build these relevance judgments, but we need to consider some possible biases, some possible problems, and in particular, the most important bias that we need to avoid is the position bias. So what that means is that the users will tend to click on the first results even if they are crap, even if they are not good, just because they are in the first positions. And in order to avoid this, we actually can build, as a click model, we can use a Bayesian network, which is incorporating some prior beliefs on what are the users' behaviors. And we can basically use, in particular, something which is a dynamic Bayesian network to actually overcome these biases. And this will result in a relevance score for pairs of queries and documents. And we can basically apply these scores to re-rank our results. So I will give you like a real-world example of what we did at AMBOSS with this model. So imagine a user is searching for STAT, S-T-A-T. This is an acronym. It stands for Signal Transducer and Activator of Transcription Protein Family. Some doctors might know what I'm talking about. I have no idea. There is a result here. You probably don't see it very well from the slides, which is Jack Stat. This is the most relevant result for this query. So whenever someone search for stat, this was like our previous search result page, and we noticed that from the data that many users will click on this result, which is ranked on the number 3, right? So it's the third result on the list. And now we basically, losing this data, we re-rank this. So we actually apply a re-ranking algorithm on this, which will push up the result to the rank number 1. And this is after the learning to rank based on click model. We actually now we're able to show to the new users the most relevant result to the first place. And we have some other examples for congenital heart defects. And yeah, you might wonder, okay, did it actually work? You remember I showed you before the rank evaluation metrics. And this little kind of graph going up in this part, it actually proved that for our queries that we used as a test set, we actually seen an improvement of 5% precision, which might sound little, but actually is quite big for this type of problems. And yeah, so we're very happy about the results of this. So what's next? This is only one example of applying AI-powered techniques to the search, but there is more. And the most important example is semantic search. So the search is built on the inverted index, right? So we have seen that we can only search with the terms, with the keywords that the people actually search for. So if I use the word hearing loss, I will get a result, which is the most important, which is the most relevant result for AMBOSS. So we have an article at AMBOSS which talks about hearing loss. But there is a synonym for this, which is deafness. But when searching for this, it will not return this hearing loss sample. And yeah, there is like confusion, right? Why is that? And the reason is that we don't know. So the engine is not smart enough to know that these two terms, these two queries are actually the same. And the semantic search is referring to the kind of the possibility of building these connections to understand that hearing loss and deafness are actually the same thing. And we want to basically get to this point. And we have several techniques of doing that. And the natural language processing is helping us here. And we basically can use query expansion, which is basically we take a list of predefined synonyms, and we basically, every time someone would search for deafness, we would also search for hearing loss, because we know that these are actually synonyms. But we can also use a knowledge graph, something externally. I will talk a little bit about it after this. Or alternatively, we could actually represent the words as vectors, which is kind of another advanced natural language processing technique. And I think you're probably already familiar with this, because it's been very successful in the NLP research in the last days. But in case you don't know what I'm talking about, I recommend to read this article, which is actually an illustration of how word2vec is working. But the idea is that you can transform each word into a vector, and the vectors which have a semantic similarity would actually be also very close to each other. So the vector of king would actually be close to queen, but also there are some interesting properties of these vectors. So you could actually compute some operations with them. So the idea is that we can basically transform the words as vectors, and then we actually, instead of searching with the words, we could actually search with the vectors and see which vectors are closer to the others. And actually, this will give us better results. And in a good word embedding system, searching for deafness would actually, the vector for deafness will be very close to the vector of hearing loss. And this would allow us to actually perform the semantic search. And at AMBOSS, we're starting to do this, but now we are using something a bit more elementary, which is a character bigrams. So we represent the words as character bigrams vectors, and then we compute the similarity. These allow us to basically solve issues like linguistic variance. So someone search for the plural form of some words, they will be very close to the original word. We also experimented with other ways of actually producing these word embeddings, which are used in the context. So the words which are very close to the others in the sentence, and BERT, which is a way of actually getting these embeddings. And yeah, I mentioned before the knowledge graphs, and this is also a very powerful idea from AI and natural language processing. The idea is that basically we can build, or to say it in a different way, someone has already built some crazy knowledge graphs of the medical world. So you have a concept like hepatitis A, and which is in a node, and you have some edges which go out and in to this node. And for instance, you know that hepatitis A is causing acetaminofen. But the doctors here might disagree, or I'm saying something very wrong. I don't know, but you understand. Like, it's actually connecting some concepts, some medical diseases or symptoms, to actually other concepts, and each edge, each kind of arrow between the nodes, it contains the kind of the action that node is acting to the other node. And so this is in few words what a knowledge graph is and what a medical knowledge graph is. And the idea is that we can actually integrate this into our AMBOSS knowledge base, and this would allow us to actually solve different problems. So it will fix some of the problems with the semantic search that we have seen before. So because we would have multiple connected terms for each medical entity, but also would allow us to immediately answer some searches which are done in a kind of action and noun form. So imagine someone which would ask, what is causing hepatitis C, for instance. We could actually take hepatitis C as the kind of the node of the graph, and actually will go into everything that is causing that, and then return that as result. And this will basically allow us to go more towards this decision support system that we want AMBOSS to be. And of course, this has some challenges because it's not so straightforward to actually integrate this basis. But we are also working on this, and we kind of expect to see some exciting results about it. And also wanted to show you like a sort of a prototype that we developed in our team. So imagine someone would search for hemoglobin reference range. Hemoglobin is like some blood value, right? And doctors, they always forget what is the range in which this value should be to actually be healthy, right? And basically searching for this would return directly the reference ranges for women and men, and we could use this to kind of give the immediate answer as a kind of knowledge card to the doctors. And one of the other techniques that we are also interested in is the personalization of results, because we know that users, so my search and Claudia's search can be very different, right? And as an example here, I put Spotify, and this is like when I'm searching for, I start typing RAD on Spotify, I get as a result the Radiohead, because I listened to Radiohead in the past, or I listened to music connected to Radiohead. But if Claudia is searching for RAD, because she listens to a lot of Latin music, she will get like this radio hits 2020, which is like more like a kind of earth type of music, right? So we will see like some difference, and this is like the same search, different results, and that's kind of the personalization. How this apply to AMBOSS? Actually, we have a very basic personalization, which is based on, as I told you before, we have students which are using our platform, but we also have physicians, and we can apply like a basic. We are already applying a basic personalization if the user searching is a student or a physician. And the kind of a potential problem of the personalization is it's the so-called filter bubble, which it means that the user would actually live in their own bubble. They will not see results from outside of it, and that's kind of something that we need to consider when building search engines or recommender system. And then finally, the last thing, which I think some of you already is working on, it's actually to automate question answering. So actually to be able to answer to questions which are posed as in a natural language. So if I ask about what's the treatment for diabetes, I would like to get like an immediate answer, like something which is very clear, or what are the complications of acne and stuff like this. And we have developed a prototype at AMBOSS in which is basically using a BERT model to actually answer this. And imagine someone is indeed asking what are the complications of acne. We create basically we use this system to actually get a series of answers, which, as you can see, they are basically taken from understanding the context of the sentence. And in particular, like in this case, scarring, it's something which is mentioned inside our content as a potential complication of acne. And the idea is that we would basically suggest to the users the immediate answer to a question which is posed as a natural language question in this case. And this green part here is actually coming from our content, where the doctors have kind of specified the scarring as a potential complication for the acne. And this is what we would suggest. So we are still trying to, this is still a prototype, as I mentioned, but it's something that we are kind of excited about it. And we are using an open source project for building this, which is Haystack. And it's actually two-phase. We have a retriever, which is Elasticsearch, as we currently use it. And we also have a reader, which is this BERT reader, to return what is the answer based on the question. So is that all? The field is always evolving. So I just want to finish showing you this example. So in 2018, so 5 years ago, no, 3 years ago, you would use Google and ask the Eiffel Tower address, and these will be the results that you will get. And actually, to get the Eiffel Tower address, you will have to click and link on the second result, and it's not even that clear. Now, when asking for where is the Eiffel Tower, you immediately get the answer here. And this is like in only 3 years. So I can imagine that the field is evolving, and the search engine in 3 years would actually look even differently. And this is indeed like you have the immediate answer, the navigational questions, and many other AI-powered features as the ones that I showed you during this presentation. So I don't know. I hope this sounded exciting. And in case you wanna kind of fix and work on this problem, we have some open positions in Berlin and in Cagliari, and we also have other problems, other things we want to solve. And so, thank you very much. So, domande, anche in italiano se preferite, o in inglese. Sì.
Thank you for the presentation. A few questions I was interested on. Type of frameworks you use, I'm not sure, I mean, I read like 10 minutes later, so I'm sure if you already mentioned them, like PyTorch, TensorFlow, this kind of stuff.
Yeah.
And the infrastructure, I mean, how is it,
yeah.
by the backend, how it looks, what type of technologies you're leveraging for
yeah.
this kind of problem?
Yeah, so we are using, as backend, we are using a Python service. And the Python service is communicating via GraphQL to our front ends. So both the actually the native apps, so Android and iOS, and the web platform, they're actually using GraphQL to actually to connect to the service, to the Python service, which is then connected to Elasticsearch, and which is our storing of documents. And we are connected, we are actually, every day, we are updating the sources based on the new information that is created in AMBOSS by our editors. We put it in Elasticsearch, and then we use our service to return the results. And the kind of the AI part is happening in the service. So we're using the results of Elasticsearch, but then we apply some NLP stuff or these re-ranking things, which I showed you, on the Python part. And for doing that, we're using Spacy for the NLP part. So Spacy is a library of Python which understands the language and give you like the sort of what the entities you have, but also some other information, right? And for the kind of the model part, we're using pandas and scikit-learn, the kind of the usual stack for machine learning in Python. We're not using PyTorch, unfortunately, but we also tried for BERT and these things. Yes, that's on PyTorch. Yeah, but that's more like experimental, not in production. Yeah. Bye.
You were mentioning at the beginning of the IDF, then we have to learn to rank. Maybe I missed. Are you using now learning to rank? And my question is, do you use TF-IDF in case you don't have accurate ranking? So you can recognize that perhaps from a statistical point of view, you don't have enough information to learn accurate ranking. So we have a fallback.
Yeah, it's exactly like that. So we're using a combination of both. So we're using the TF-IDF scores, and then we apply the re-ranking on the first n results of the TF-IDF score. So to kind of avoid that new things, new documents might not be seen. But in case we haven't never seen the document, we apply some sort of default re-ranking score. And also, in case the query is new, something which was never seen or very rarely, we use TF-IDF as a fallback. Yeah. So it's a combination of both. Yeah.
You showed that Google, to me at least, appears like a data. It's going to be getting like a database. I mean, you use natural language to query a database in many cases, like you did. Okay? Looking for the attribute, for the column address, for the raw
Mhm.
FL data, right? So I wonder in which point you are integrating knowledge bases in your search, because you mentioned it in customer search, etc. But for instance, I didn't get to whether you try to tag the question
Mhm.
looking for entities in a knowledge base, for instance, before trying to answer.
Yeah. So
Or
we already have a knowledge base which is used in AMBOSS in different parts of the product. So the idea is that we want to, and it's already working somehow. So as I've showed you at the beginning, searching for asthma, for instance. Let me go back to this. It's returning this immediate result, which is kind of similarly to what Google is doing when searching for the address of the Eiffel Tower. But this is a very basic knowledge base, which doesn't allow for more complex queries and questions as we've seen. And we want, the idea is that we will integrate this with the external knowledge base, or we want to modify our existing knowledge base to actually support other types, other structures. And I think we can do this in both ways. So we can use AI and NLP to actually support the creation of this base, and then which could then be, and then we will use our medical doctors to actually confirm that the results of this are good, and then we would use this as it is. Or we can, at the same time, we could also use something as BERT to actually search inside our content and understand what are the different parts, understand what is the context, and what are, looking at the asthma complications, for instance, we would use the asthma article of AMBOSS and check immediately what are the complications. So we are trying different things here. We don't have a definite answer yet on what type of, but I think will be potentially the combination of different technologies applied in different parts of our product. That's it.
Maybe a curiosity question. So, I work in practical physics.
Okay.
So completely different. But we use machine learning in the same, like in a similar way. But we tested a lot of different ways of applying the different architecture of machine learning to the same problem. I was wondering if you're doing the same, or if the supervised learning algorithm you use is something that maybe you know that it's the right one.
Yeah. So in my experience in applying AI in products, I've seen that in industry, it's actually data is more important than machine learning method, and I think this is where actually the main difference between industry and academia is actually, because I think in academia we spend a lot of time and in improving the methods and different algorithms, or changing some layers of neural networks. Why we have seen in applied AI that the data is actually the real gold here. So we are trying, and the example of the click model, I think it's actually a good example of this, where we could actually use learning to rank as a classical supervised machine learning problem, but instead we decide on focus on the data and how we do collect the data, and how we can understand when the signals from the users represent something good or not. I don't know if it answered the question. I made more philosophical. That might be.
I think I was also wondering how much data you have, because it seems that you're working with like a small set.
Yeah, I mean, but we have many users, and as you see, so many users that are using the search functionality, and we're trying to leverage that as best as we can. But
We have a question from
yeah.
Facebook. I don't know if you can see the question or I
Can you say the?
Okay, yes, it's about if system manage different languages and EBS, how the languages is handling machine learning. So for machine learning, applying languages. Yeah.
Lab values? No.
Languages.
Languages.
Yes, AMBOSS platforms support different languages.
Yeah. So for now, we're working on with two languages, which is English and German, and we mainly support we support right now only these two languages. Uh, I think that for English there is more NLP libraries out there, so we can actually apply more methods for English. So the English search engine is slightly more advanced than the German one now, because we can actually use some functionality of spaCy, which, for instance, are not available for German yet. And an interesting aspect from using the data and using the queries is that we also have, AMBOSS is used in every country of the world, and some people search in different languages. They might search with Spanish, but then they would refine their query in English. And then an interesting side effect, let's call it like that, of using the data is that actually we can actually use the kind of the information and the previous queries of other users, which might have tried to use AMBOSS in Spanish and didn't get any answer, but then refined the search in English and then use that to actually support and basically to understand Spanish as well, even though our content is not in Spanish. But
congratulations for the presentation, a very interesting one. I'm always excited when I see AI software working in production. I'm wondering if you have bottlenecks, performance bottlenecks. For example, I know for sure that that is very difficult to use in production.
yeah.
If you know others, can you mention that?
Yeah. So that's a very interesting question, because users, they are very spoiled when it comes to search. So they expect in the results to be there in basically real time. So everything which is more than 200 milliseconds, it's bad. So we cannot produce a result in more than 200 milliseconds. Otherwise, the user might get pissed, to say. And this is an interesting problem, because, of course, some of these methods, and BERT is one of them, it takes a long time to process. And that's why we use these kind of two-phase approaches in many of these problems. And also for the question answering prototype, which I showed at the end, we are using this approach. And the idea is that the idea is that you have a first step, which is a retrieving step, which is based on a TF-IDF or other kind of traditional scoring systems. And these basically allow you to actually go from all your documents, which might be thousands and thousands, to only a handful of them. And basically, and then you would apply BERT and other more advanced technologies only on the candidate selections, which has already been made by the retriever part. And so, yes, this is the biggest bottleneck, and this is how we're trying to solve it.
So you have suboptimal results.
Yeah. 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 Yeah.
Only you can find this only training version.
Yeah. So we're using indeed like transfer learning, which is the kind of the best way to train BERT. We start from already trained BERT models, and we apply it to other medical texts, which not necessarily are our medical, but they can be like other open library, open documents, and so we're using this to make the BERT model more adapted to the medical domain. There is already a bunch of medical BERT models. There is something from Microsoft, which has been trained on PubMed articles, which is like a general medical kind of repository of medical articles. I haven't had the chance to try that yet, but I think this is something we will try soon, pretty soon. Altre domande? Bene. Certo che sì. Chiudi te qua. Ok. Io chiudo direttamente così.